in the next subsection, we'll see how we can use arrays to build something that feels like the lists in Python, that they can grow as large as they're needed. And while many of you will have seen this, I think the analysis maybe you haven't done formally, and it's just such a vital thing that everyone should know what happens under the hood for Python lists and other such resizable arrays. That's the name of the data structure. Before we get to that, I want to point out that arrays themselves you could somehow see as an abstract data type if you want, because it supports certain operations. You can create one with a certain specified size that you need to know up front. And then you have two operations to read and write the array. And almost all programming languages have built-in support for this and special syntax because you use it all the time. Now, in another way, it is not really an abstract data type, because when people talk about arrays, they always have a very specific implementation in mind. So you could sometimes try to re-implement an array in a different style. But because they're so basic, it's often not really possible. I've heard this nice saying that arrays are like the sharks of data structures. They've been around forever. They're somehow crude and a bit primitive, but they're still efficient in what they do. And so they probably survive till the end of time. But we need lists, or we need collections that can grow. So how can we get the efficiency of an array without the extra pointers and the random access, with at the same time being able to make them as big as they need to go without knowing it up front? We can do that with a standard trick. So, and I'll explain it in the way you would implement a stack, but the data structure is actually more general. As before, for a stack, we had an array that contains all the elements. We called that S. That was this upside down or flip to the side array. And we maintained this position in the array top. It's just an index, but I'll draw an arrow because it's nicer to see, which tells me this part is currently in use and the rest is empty. That's what we had before. Now we'll additionally have another thing that we maintain, which is that this length of S, the capacity, is somehow related to the number of elements we have in the array. We want that the array is always, well, it's never over full. We can't really do that anyways, but also it shouldn't be too empty. Okay, if we can guarantee these two things, then we can always use the array. So we can always push more elements if that's guaranteed afterwards. But the question is just how do we do that? Let me point out, we've seen this term invariant before when we talked about proving the correctness of programs and loop invariance. It's a more general notion. So in the loop invariant, it was a certain condition that was true before the loop and at the beginning of the loop and at the end of the loop body, and then iteratively or by induction throughout the loop and after the loop. So it was almost true all the time, with maybe a short transition period while you were executing the loop body. And the same notion is very useful in data structures as well. An invariant is something that is supposed to be true at all times, maybe with the exception of the time during an operation. While an operation is executed, you're allowed to violate it, but then once the operation is finished, you have to guarantee it again. And that's a powerful feature to prove that your data structure works. If you don't have an invariant that in the end implies that the operations work well, you likely haven't understood how the data structure works, or it's not actually correct. And so we often list invariants like this as a way for you to understand what happens, and also as a way to check if you followed everything correctly in the operations. So here we'll have these three invariants. Once you have this, and I promise you they are able to maintain, it should be easy. At least in this case it is. So the first two are easy to maintain from the code you've seen before. But for the third one, we have to do a little work. One way to do it is like this. Before we do a push, we check if the array is full. And if it's full, we double its size. And after a pop, we may have emptied the array too much. So if then now the new size is too small or the array is too big, then we'll also allocate a new array with size 2n. So this looks like it's doubling, but it's actually shrinking because n is the number of actual elements. This simple trick has different names: doubling arrays or resizable arrays, dynamic arrays sometimes. They're all a bit misleading. The arrays don't really resize. We just allocate a new one. But it feels like we're resizing the array. The important bit to note is it doesn't come for free. We have to copy all the elements. If we allocate a new array, it's initially empty, so we have to copy all the elements that we had previously to the new array. And that takes time. So is this really a good data structure? For those who've seen this before, let me ask the question here first. If you haven't seen this trick, there's no way for you to know this. So in that case, you can just guess and see what you feel intuitively should be true. Okay, we'll come back to that question. So I won't show you the answers yet. But I'll basically show you what you need to answer the question yourself. And maybe we can quickly keep so if you roughly look at this, there's roughly a quarter of people who think each of the statement is true, right? Something like that. So what comes up in this context is something, again, that's more important than in this concrete example. So I'll try to be not too quick on that part. And that's called amortized analysis. The idea behind this is that some operations in our resizable arrays will be very expensive. If I have a push and I have to double the array, I have to copy all the contents of the array. So that's linear time for the copying. That's really expensive. Arrays were much faster if I didn't have to do that. And likewise for pop, if I have to shrink the array to a new one and copy over. So that sounds bad, right? We've made something that was constant time, linear time. That's horrible. I argued earlier that if you do insert in the middle of a list in Python, that's an expensive operation that you shouldn't do, at least not if you want to repeatedly do it. So how does that match up with otherwise lists being fast? The point is that if you have an expensive operation, it means that many other operations that follow will be cheap. And so you can amortize the cost you had for this expensive operation over many cheap operations. So in a way, the cheap operations pay for the expense for the expensive operation. That's the intuition, but what does that mean formally? And so, okay, don't get too scared by all the text. We'll go through it. again, things you've seen before, we'll use something like a potential function. And you can think of this like a bank account. When an expensive operation happens, you're in debt, and the cheap operations have to pay that back. Or sometimes the other way around, you have cheap operations, and they pay an extra deposit that the expensive operations can then use. If at the end of the month your account is in reasonable shape, it doesn't matter how it went up and down in between. At least not too much if you just look at the overall outcome. That's the idea. And again, finding the potential is sometimes tricky. This one is motivated by the following idea. If this is your array, S, and it has length C, right? So it from end to end can hold C elements. Our stack will only use a certain part of it. That's the actual elements in the stack. Or we do it like this again. So there's n elements in the stack that we currently use. Now there are two magic thresholds where we get active. One is when the number of elements reaches the capacity. And one is when it is just a quarter full. So here we have the mark C, and here we have a quarter of C. So that's when things get expensive. So the intuition behind this potential is we take the distance from where we currently are to this one expensive point. That's n minus a quarter of C, right? And we have C minus n, that's the distance from the other end. And whichever of these is smaller, that's our potential. So we kind of, if you think of it in this bank account statement, it means we have a lot of cheap operations still to come before something expensive happens. It's kind of a budget that we still have, or a balance. Now you can analyze what this function can be. It can be 0 at the point where you just exhaust the array, or you just fill it to the minimal threshold. And you can show it's at most 0.6 n. That basically just comes from our invariant. We require C to be between n and 4n. And so if you find where this is equal, you just set those to equal. And then you get that the maximum value of the potential is this 0.6 n. Okay? Now, why does that potential help in any way? What we'll do is we'll analyze each operation in an amortized sense, where we take the amortized cost to be the actual cost, what it really costs us to do the operation, which in our case will be counting the number of array accesses, which is just one or so if we just do a push or a pop and don't have to copy. But we might have to do many more if we have to resize the array. But then the amortized cost also takes into account the change in potential. And why this is multiplied by 4, that's just to make the math work. There's no easy way to see this. Let me briefly go through the 3 different cases that we have. So we have the option that we do a push or a pop where we don't have to resize the array. The actual cost is just one array access. I just get the element, or I overwrite it. But this might consume a credit. So I might move the current mark of how full the array is closer to the red boundary. I said I might. It might also increase if I move away from the boundary. This depends where I am. Here I'm roughly in the middle. But if I have something like this, the array is almost full, but I remove an element. So now the new fill is only up to this point. I've actually increased the potential. But that's all right. In the worst case, we are one step closer to the boundary. And so the potential might shrink by 1. If you multiply that by -4, it means a +4. Okay, so the amortized cost is at most 5. And the units here are just array accesses, if you want. That's the first option. What can also happen is we have a push, and we have to double the array size. Then the actual cost is 2n plus 1. So you can work this out. If you allocate the new array of size 2n, you have to copy n elements, but then you have to read and write them. So that's each n accesses. And you still have to do the actual push you wanted to do. That's the plus 1. So that's the actual cost, is a lot. But if this happens, I claim that it creates a lot of credits. Now, how does that work? Let's do this one in a bit more detail. So if we have a push that's expensive, the situation before must have been the entire array is full, n equals c. That's before. And after that, we've doubled the whole thing. And it's half full plus 1 element, right? And in the new array, these two marks at the new c and the new quarter c, they're actually far away from the new border mark. Indeed, this is the new n, and we're away by essentially half n. Okay, that's why you get that extra credit. And the plus 1 comes from, well, we're not really at this, but we have one further to the right. So if you take the distance between this and inserting what the capacity is, namely 2n. So here, n is the old size, and the new size is n plus 1. I just added one more element. Then a quarter of 2n is n half, and the distance to n plus 1 is 1/2 n plus 1. Okay? So I have to add the actual cost, and then minus 4 times the change in potential. But minus 4 times this is minus 2n minus 4, which magically happens to come out at, again, 5. Okay? So 2n plus 1. The 2n just cancels. And then I have what's left is the 1 and plus 4. Okay? So again, the amortized cost is at most 5. We have a third case, that's the pop. That's very similar indeed. By analyzing when the pop happens to be expensive, well, it only can happen if we're at the quarter full. Now we shrink the array to half the size. Okay, my drawing is not to scale. But now this was n is 1/4 c. Afterwards, I make my new c to 2n. So that means I'm now half filled, and actually 1 less, because I pop 1 element. And so again, the distance to the critical marks, 1/4 c prime, which again is n, quarter n and half. So again, the distance here is roughly 1/2 n. I get the minus 1 in this case because I'm one more to the left. So by essentially the same calculation, you again get a cost of 5. Okay, basic math here is not working. Previously, the cost is the minus I didn't do correctly, but it's at most 5. That's the part we need. And in this case, it's exactly 5. So the slides were right. So, okay, great. Let's come back from this deep dive. Like, why did we discuss amortized costs? What's the whole point there? We've shown if I take the operation and I add the actual cost and the change in potential, I always get a bound of at most 5. So what we do now is we take a sequence of operations, say m operations, and what I'll sum up here, that's the amortized cost. And I know that I've defined this as the actual cost. So each of the AIs is the actual cost plus the change in potential, minus 4. And we'll just write phi 1 minus phi I minus 1. So that's the potential after operation I and the potential after operation I minus 1. Okay. Now this type of sum has a special property. It's called a telescoping sum. Because you see a term appears positive for one I, and for the next I it will be negative. So we can split this sum up to be the sum of all the CIs. And then we have minus 4 times the sum, where we always have the previous term minus the term before. And that completely goes away except for the first and last entries. So this is the total cost, the actual cost. And what's left of this is the potential at the very end minus the potential at the very beginning. Every other I appears both positive and negative, so it just cancels. That's one side. But we've also upper bounded the amortized cost in each case by 5. So this sum is at most 5 times m. Okay? And so if you take this inequality and rearrange it so that you get the sum of the actual cost on one side, then that's at most 5m plus this part. And at this point we use that we have a bound on these. So let me spell it out. So it's plus 4 phi m minus 4 phi 0. Now, if we want an upper bound on this, we can take the largest value that phi can use in this case. And remember, it was at most 0.6 n. And it's at least 0. So if I subtract nothing, I only make it bigger. Okay. And so that's what's summarized on the slide. If you take any sequence of m operations, no matter what they look like, the total actual cost is at most what's spelled out here. And you can say that's in theta of m plus n. So it's linear in the number of operations, but it's also linear in the final size of the array. And so, well, if you start with an empty one, the two are essentially the same, or m is bigger. So let's come back to that question. I'll show you the answer. There's only one that's really true. So the elements are not always stored in an array of size 2n. It's size 2n at the point where we resize. But then n can change, and we keep the capacity for a while the same. Adding an element at the end doesn't take constant time in the worst case. It's only amortized. So if you do many operations, it takes constant time. But it could happen that this element you add is one that triggers the doubling, and that takes linear time. The last one is even worse. If you don't say where you insert or delete, it could be in the middle of the array, and there's no way to do that in constant time. Only at the end in amortized sense. And the amortized sense spelled out is the third answer. Any sequence of operations means that on average the operation was cheap, but every individual one could have been expensive. So whenever you use lists in this sense, you have to keep this in mind. If it's a real-time application where every operation has to be fast, you can't really use the doubling array trick. Then you have to think of something different. But for almost all use cases, it actually is a good trade-off because you're not doing one single operation. You're doing many operations on the arrays, and then it amortizes out nicely.